Here minus 2 plus j3, it is a point of interest, so we took it as S1. And here you have poles at minus 1, minus 2, minus 3, minus 4 are zeros. Now minus 2 plus j3 is the point of interest, we have marked it as S1. Now consider minus 1 to S1. So here the angle is moving to the left and up, so it will be 90 plus tan inverse 1 by 3, because horizontal is difference is 1 and vertical difference is 3. So on the horizontal axis you have negative and vertical axis you have positive, so it lies in second quadrant. So you took angle as theta 1 is equals to 90 plus tan inverse 1 by 3. Theta 2 minus 2 plus j3, it is obviously 90 degrees, so no need to use tan inverse y by x term. Now theta 3, horizontal distance is minus 2 plus 3. Minus 2 minus of minus 3 you will get plus 3, minus 2 plus 3 1, and vertical distance is positive 3. So both are positive, it will be in the first quadrant, so directly take it as theta 3 is tan inverse y by x. Now theta 4 to S1, minus 2 plus 4 you will get 2, so horizontal distance is positive and vertical distance is 3 minus 0, you will get 3 positive, so it is also positive, so both are in positive, so it will be in the first quadrant, so you will get theta 4 as also tan inverse 2 by tan inverse 3 by 2, opposite side by adjacent side. Here g of s is given as 1 by 1 plus st1 into 1 by 1 plus st2 into 1 plus st3. This is a type 0 order 3 system. So type 0 order 3 can be represented as shown in the graph, with head in the second quadrant and tail in the fourth quadrant. So it represents type 0 order 3. At point x on the negative real axis, phase angle is minus 180 degrees and omega x can be written as under root sum of the 3 time constants by product of the 3 time constants. And at point y on the negative imaginary axis, omega can be determined by 1 by under root t1 t2 plus t2 t3 plus t3 t1. These are the important conclusions used here in the root locus diagram. If low frequency minus high frequency phase angle difference is positive, then polar plot ends in clockwise direction. If the difference between the low phase frequency and high phase frequency is negative, then polar plot ends in counterclockwise direction. So in other words, it is known as tail. Tail can be represented by minus 90 degree into type. Now third point, if finite 0 is nearer to the imaginary axis, then polar plot starts in counterclockwise direction. If finite pole is nearer to the imaginary axis, then polar plot starts in clockwise direction. It represents the head of the polar plot, which we can also write as minus 90 degrees into p minus z. phase margin is equals to 180 degrees plus angle of g omega. Phase margin formula is equals to tan inverse 2 eta by whole under root minus 2 eta square plus under root 4 eta power 4 plus 1. When eta is less than 1 by root 2, then eta is approximately equals to 0.01 into phase margin in degrees. How to find transfer function from the given Bode plot, magnitude plot? If the initial slope is 0, then it is a type 0 system. K is 10 power m0 by 20, where m0 is the amplitude magnitude of type 0 system. In type 1 system, initial slope is minus 20 degrees. So if you extend the initial slope and cut it at the real graph, you will get omega 2. Gain K will be omega 2. For type 2 system, initial slope is minus 40 dB per decade. So if you extend that initial slope and cut it at the real axis, you will get omega 2. Now gain K will be omega 2 square for type 2 system. In this Bode plot shown in the figure, he has given magnitude as 36 dB, minus 12 dB, minus 21 dB, and he has given the frequencies omega 1, omega 2, omega 3, and he is asking to find the values of omega 1, omega 2, omega 3. See, initially the slope is minus 20 dB per decade, means minus 20 dB per decade is equals to minus 6 dB per 1 octave. Minus 40 dB per decade is equals to minus 12 dB per octave. Here we do not know the values of omega 1, omega 2, omega 3. So initially we can take the reference value as half. Now there is minus 20 dB per decade, means magnitude gets subtracted by minus 6 dB. 36 minus 6, you will get it as 30 dB per decade. It is an intermediate value. In asymptotic Bode plot, we did not consider the intermediate values. So we will take another step, that is 30 minus 6 dB per decade, that is 24 dB per decade. Note this point, if there is minus 6 dB per decade, multiply it by 1. If there is slope drop of minus 12 dB per decade, you should multiply by 2. From 36, there is a drop of 6 dB per decade, but we will get the intermediate values of 30, so we will ignore, and again 6 we will minus, and you will get 24 dB per decade. So from the initial magnitude 36, you will drop to 24 dB, which is minus 12 dB per decade. So if you multiply omega 1 is equals to half with 2, you will get 1. So at magnitude 24 dB per decade, you will get 1. Again next slope you have minus 40 dB per decade, which is minus 12 dB per octave. So if you subtract 12 from 24, you will get 12 dB per decade, and on x-axis you will multiply with 2. So 1 into 2, you will get it as 2. At omega is equals to 2 radians per second, you will get 12 dB per octave. And next, from 12 it is going to the magnitude 0. Again 12 dB you are subtracting, so that you will get 0 dB at omega is equals to 4. From 0 it is going to minus 12. So again minus 12 dB is subtracted, and you multiply this omega is equals to 4 into 2. You will get omega is equals to 8. And by using the slope formula, slope is equals to y2 minus y1 by x2 minus x1, and by using the log terms on the magnitude axis, you will get omega 3.